Dear colleagues, please take your seats. We will start from the first lecture. So I'd like to introduce Gleb Barashov from 12. Please, Gleb.
Thank you. Good morning, dear colleagues. Glad to see you. First of all, I would like to introduce myself, Head of Direction, Project Management and Business Development Department, 12. Since 2012, involved in decommissioning. And for these 10 years, I successfully performed several projects in Russia, such as decommissioning fuel production in Novosibirsk, decommissioning storages of radioactive waste in Angarsk, uranium isotopes production в NEM Moscow, and another hazardous facilities. Now I am a curator of Decommissioning Competencies Center in Angarsk. We created in 2019, and now it is one of the leader in radioactive metal waste processing, radioactive waste management, and as a general contractor, perform biggest projects in Russia. My colleagues asked me to prepare 3 reports. First is related to aspects of comprehensive engineering and radiological survey. This report mostly theoretical, and 2 others related to dismantling and decontamination, processing equipment, and building structures of nuclear fuel cycle facilities. It's mostly practical works and examples of real performed projects in recent 2 years. So let's start with comprehensive engineering and radiological survey. Start with general information and then tell about methods, tools, and approaches to CARS. To do it less boring, I removed all information about normative documentation to do it more interesting for you. Next slide, please. Well, conducting a comprehensive engineering radiation survey for decommissioning is a necessary and critical information at the final stage of the life cycle of the facility. Based on the results of CERS, the operating organization ensures the development of design documentation for decommissioning and prepares a decommissioning safety justification report, which is required to obtain a license for decommissioning of the object. Conducting a CERS includes a set of activities requires for the development of design documentation for decommissioning and aimed at obtaining information on the engineering and technical conditioning of buildings, structures, equipment, system, as well as on the radiation situation in the premises and the nuclear plant site, and includes information on volume and surface contamination with radioactive substances, and qualitative and quantitative composition of radioactive waste. It is better to have data on the actual condition of equipment after it has been brought to a nuclear safe state. Radioactive media have been removed from systems, equipment, pipelines, and decommissioning has been carried out according to standard technologies. Operational organization do it at the zero stage of the object. It is possible to formulate the following basic principles and approaches to the CERS tasks procedure and timeframes, as well as a requirement to the structure and content of the report of the CERS result for the nuclear plant decommissioning, and is performed to assess the actual technical radiation status of system, equipment, building structures, utilities, and of course the territory of the site, as well as the volume and aggregate state of accumulated operational radioactive waste and generated radioactive waste during decommissioning. What else? Also, I would like to say that aggregate state of accumulating operational RV affected of the safety of personnel, environment, and population. Also, it is conducted to develop and submit to the regulatory authorities the necessary documents for obtaining a decommission license. It is based on results report, decommissioning program, decommissioning design documentation, safety justification report, and others. The scope and task of CERC depends on decommissioning strategy being implemented based on the decommissioning option adopted. We have different examples in the. It depends on strategy we choose. In the immediate dismantling strategy, the role of radiation survey is greater, and in the delayed dismantling strategy, engineering surveys is greater. Based on this, it can be concluded that a comprehensive engineering and radiation survey is the information base for selecting a specific decommissioning option, as well as for developing decommissioning design documentation and safety justification report. The whole information, general. Next slide, please. The information basis for the organization, preparation and conduct of the CERS for decommissioning is construction design documentation, operational history, technical condition data, and annual status reports, which prepared operational organizations. In order to justify the choice of methods and scopes of CERS facilities are usually categorized. by functional purpose, by provision of decommissioning works, by safety class, and by conditions of location and different radiation exposure and control zones. It's a general scheme. What else? Next slide. The time frame of for conducting the CERS for decommissioning is influenced by organizational, methodological, technical arrangements for specific types of survey carried out as a part of this comprehensive survey. General program is developed for the comprehensive survey. The CERS program contains a description of the forms of conducting different types of survey, composition of preparatory works, and missions for their implementation. The objectives for development the overall CERS program are to determining the timing of the list of activities, defining a list of organizational and other documentation, including measures to ensure the safety of personnel involved in survey, determining the materials and equipment that are needed when carrying out the work. And when we organize this work, we created a team group, and it may include representatives of specialized relevant organizations and enterprises, as well as personnel of operational organization. Site plan. And now we'll speak about engineering and radiological survey separately. Starts with engineering survey. The main objective of engineering survey is to assess the technical condition of building, system, equipment, and metal structures, building construction, and so on. At the stage of preliminary inspection, the categories of technical condition of the construction, depending on the existing defects and damages, should be established by external science. What types of conditioning there are? Normal, good condition, no visible damages and cracks of the building structures. Satisfactory condition, minor damages, and unsatisfactory condition when damages, defects, and cracks evidencing limited work order, and emergency condition, and it is when existing damages evidence that structures are unfit for operation and pose a collapse risk. In the next lecture, I will tell you about the project in Angarsk, uranium isotope production decommissioning, and we look at preliminary inspection and detailed survey, how it affected on cost and time frame of the project. Based on the preliminary inspection, work program for the detailed and survey should be drawn up. Detailed survey is carried out to obtain initial data for verification calculations. And the result of comprehensive engineering survey: assessment of technical condition and residual life of main buildings and constructions, assessment of the technical condition of building structures, including their residual life, assessment of the technical condition of physical barriers, preventing the spread of radioactive waste, of radioactive substances. What about methods of engineering survey? There are destructive methods. It is a shear test method or method of statistical control of concrete straight and homogeneity. And the most used non-destructive methods are ultrasonic inspection and acoustic emission methods. What about comprehensive radiation survey? The main objective of it is to obtain representative information on the radiation characteristics of system, equipment, building, concrete and metal structures that had been exposed or have been in contact with radioactive media. What we do? Determine the activation level of equipment, determine the level of composition of surface contamination with radionuclides of building structures, system, rooms, and other premises, to determine radionuclide concentration and composition, to assess of radionuclide concentration, composition in the air of working premises. And the result of comprehensive radiation survey, it is the radiation status and level of radioactive contamination of the territory of our site, activation level and radionuclide composition, a mass and characteristics of radioactive deposits with system, equipment, and pipelines, aggregate state and classification of radioactive waste accumulated during operation and generated during decommissioning. Techniques and methods and tools. Information of radiation situation of the territory should be obtained using approved and certified techniques on the basis of analysis of results of gamma radiation field measurements performed after the final shutdown, results of surveys, including direct and indirect measurements performed after the final shutdown, calculated data obtained using computational methods to assess the radiation status and the radioactivity accumulated in system, equipment, building, and protective structures. When conducting a comprehensive radiation survey for decommissioning, the following techniques are used. Different measurements of the spatial distribution of gamma radiation dose rate, beta and alpha particle flux density of the surface, collecting of samples, determination of radionuclide composition. The used methods should be certified. What else? Gamma radiation dose rate measurements can be carried out using dosimeters, and we control it at a distance 0.1 meter. It is maximum gamma radiation dose rate 1 meter average and 2 meters minimum value of gamma radiation dose rate. Determination of loose surface, the contamination. Determination of not fixed beta and alpha contamination on the surface by wiping method, by sampling, and spectrometric survey provides for determination of specific activity of radionuclides in samples by gamma spectrometry method. And what about current trends in the CRS field? All measurements traditionally performed manually with mapping of the facility, and it leads to data simplification because it's very difficult to combine the received radiation data with information on the actual condition of structure. Therefore, only the transition and implementation digital CERS allows to an extremely accurate digital perception of the facility and its perimeters. 3D scanning and panoramic photography are used instead of the usual manual labor. Well, this will be explained in more details by the next narrator, and he explained how digital survey implementing in digital design and documentation. Thank you for your attention. That's all. I propose to ask questions after the second and third report, because there we look at a real project with examples, with interesting aspects and features. So it will be more clarified and explained there, because our time limit is up. Thank you. Очень жарко.
Hello, everyone. Let's start our lecture. My name is Peter Matveev, and today I'm going to talk about radionuclide extraction separation. So, in my lecture, I want to give some ideas where in radiochemistry we should do these separation things. First of all, some emphasis, of course, we will make on decommissioning processes, what chemical separations we need to do during decommissioning and decontamination. And most part of my lecture will be about these certain techniques, solvent extraction, chromatography, and precipitation. And in the end of the lecture, we will see some cases from different scientific groups, what they do with some of radionuclides and some results about decontamination by these techniques. So, okay. Why do we need to separate radionuclides? In case of radiochemistry and radiochemical technologies, I think we can mark these things. First of all, is the production of radionuclides. In this point, I think we can add nuclear fuel cycle, nuclear medicine, and some other radionuclides for industry. For example, in case of gamma inspection of weldings, of steel weldings, sometimes can be used gamma sources based on cobalt 60 or cesium 137. So, okay, here, nuclear fuel cycle. As I understand, in Monday you have a lecture on this topic. So there are some parts of it where concentration, concentrating and separation of different elements occurs. First one is mining, when we need to isolate uranium from decay products and carbonic metals that occurs in ores after the dissolution. If we're talking about open nuclear fuel cycle, of course, in the end of it, we have isolation of uranium and plutonium and refabrication of nuclear fuel. And also, but in perspective, this perspective, technologies is fractionation of high level liquid waste. And here we are talking about isolation of americium, for example. Another big branch of radiochemistry is production of radionuclides for nuclear medicine. If we want to obtain some target radionuclide, every time there are two steps of production. First one is irradiation by particles, charged particles or neutrons of some kind of target by nuclear reaction. It's the first step. And second step is a chemical isolation of certain radionuclide. What kind of separation here we can have? First is from target matrix, target material. In general, their concentration of target material in the solution after dissolution of target is much more higher than concentration of certain radionuclide. And also during irradiation, we can obtain some byproduct radionuclides, and we also need to separate them from our certain radionuclide. And here you can see some different radionuclides that use in diagnostics or therapy in nuclear medicine. And another big topic, I think in case of decommissioning is the main topic. We need to separate radionuclides during their determination and analysis. Why? Because there is no universal technique for analysis, no radiometric technique that can be used for determination of every radionuclide. Why? Because there are different decay modes for different radionuclides, of course, alpha, beta, gamma, and so on. And also, there's some mutual spectral influence. And if we want to measure them, we need to separate before measurements of radionuclides. Slide. Case why it's important. Determination of plutonium-239 in uranium matrix. Here you can see data on activity of these elements and of their masses in the sample. Uranium, just 20 becquerels, but plutonium, 0.5. So excess in case of radioactivity, only 40 times. And because of the different half-life times, in case of uranium, it's 4.5 billions of years, and in case of plutonium, it's 20,000 of years. In excess of uranium in mass is about 7 order of magnitudes. Because of this problem, because of this excess of uranium from point of view of activity and mass, we cannot use no alpha spectroscopy and no ICP-MS. Alpha spectroscopy will be suffer from, first of all, that energy of alpha particles is really close in case of uranium and plutonium. Also, there are some problems with preparation of counting samples due to excess of uranium. In case of ICP-MS, there's another problem. This problem is formation of molecular ions. Uranium can easily formate molecular ion, uranium H+. So it will have the same mass as plutonium-239. And what we can do here, we can separate uranium from plutonium. And if the factor of separation is 10,000, it's possible to use alpha spectroscopy for such measurement. But it's still impossible to use ICP-MS, for example. So that's why it's important to use separation techniques during radiometric analysis. And documentation and decommissioning. First, I think one was big part during decommissioning is a documentation process. And here we need to use radiometric analysis to understand what the radionuclides in the solutions after documentation in some part of facility that is decommissioning and so on. During radiometric analysis, we should answer such kind of question: what kind of radionuclides, what are their activities, and also important point here, what species, what are the physical chemical forms of these radionuclides, because it will be useful to when we want to choose the right chemical technique for documentation. And in Friday, I have a lecture on cyclotron techniques for these purposes. And this lecture will be mostly about physical chemical forms understanding and so on. And also, after we make documentation, usually we have secondary liquid waste. And to reduce volumes of it, we can use extraction and to concentrate radionuclides and reduce these volumes. Here, kind of sophisticated general scheme for analysis. This is general scheme, so by it we can find different radionuclides from halogens here, for actinides, transuranium elements, for such usual radionuclide strontium-19, and for example, as activation product, we can obtain calcium-41. So all of this scheme works on separation of radionuclides, on separation. So, and now let's talk how we can separate or extract radionuclides. So, general point, it works not only radiochemistry, but in all branches of chemistry, all fields. We should use two-phase heterogeneous systems. For example, liquid-solid, it's for co-precipitation and for chromatography. Liquid-liquid systems, it's for solvent extraction. And gas-solid system for gas absorption methods or for some such kind of sublimation methods. And as I say in the beginning of my lecture, main chemical techniques is precipitation, solvent extraction, chromatography, and sublimation processes. Precipitation. So, when we're talking about general chemistry, precipitation process is widely used. But in case of radiochemistry, another important issue raised is co-precipitation. Why? If we want to understand if there will be precipitate after mixing of two compounds of two solutions, we should take a look on solubility product. Is a value that can be calculated as presented in the slide. And if this product is higher than solubility product, precipitate forms. And is it lower, precipitate doesn't form. Here you can see some typical values of solubility product. And when we work with macro quantities of substance, so every time, as usual, precipitation occurs. But in case of radiochemistry, for example, here's example of silver 105. It have a short half-life time, about 40 days. And for example, if you take a solution with a specific activity 1 megabecquerel per liter, it means that concentration of this radionuclide is very low. You can hear this concentration. And solubility product is here. So what it means? It means that even in presence of 10 molar acid, there will be no precipitation. And what we can do here, we can use the precipitation occurs in the presence of macro component, a carrier. So that's why in radiochemistry, co-precipitation have more use than just precipitation. And here are some examples of precipitation and co-precipitation processing in practice. First of all, the giant history sense is separation of radium and polonium by Marie Curie. It was a huge work. As you can see, there were 10,000 repetition of crystallization and precipitation processes. Also, from historical point of view, first processes for obtaining of plutonium during Soviet atomic project and Manhattan atomic project, they were used precipitation techniques, co-precipitation with lanthanum fluoride scheme and bismuth phosphide scheme. Just the point that these techniques were suppressed by extraction techniques because these techniques are continuous. We can work on it without any stops. It's impossible to make during precipitation. About lanthanum fluoride scheme is used in laboratory practice during preparation of samples for alpha spectroscopy. Another big field where precipitation of radionuclides is used is concentrating of radionuclides. Here are some examples. when we use a carrier that take up all of radionuclides that can occur in the solution. Also, another examples. Here we can see certain radionuclides, certain carriers that can remove these radionuclides from different aqueous matrices. But in general, if you're talking about co-precipitation especially, there is no selectivity towards some specific cations. In most cases, we can take up all of radionuclides, or it should be very different chemical nature of the radionuclides for obtaining selectivity during precipitation process. Solvent extraction. What is solvent extraction? Is a redistribution of component between two immiscible liquid phases. And as a rule, initially, these components dissolve in the aqueous phase. So we have two immiscible liquids. After that, we make phase contact. And after that, we obtained two phases. But in general, a component is letter A here, goes to the organic phase. And because they are immiscible, we can mechanically separate them and obtain radionuclide in one of the phases. Дальше. Yes, they are separated. Дальше. And some terminology here. First of all, in general, organic phases consist from two parts. Is an extractant. This is a compound that extract radionuclides from the organic phase. And also in general, we don't use pure extractant. We use it with some kind of diluent of solvent or organic solvent. Also, after we carry out extraction, we should take radionuclide from organic phase in the aqueous phase, and this process is called back extraction. And some extraction chemistry. There are about 4 extraction mechanisms. Why it's important? Because by different mechanisms, we can extract different radionuclides in different physical chemical forms. So it's important to understand what extractant we should use, and this information is based on the nature of the radionuclide. First mechanism is simple physical distribution. There are lots of compounds that are more soluble in organic than in water. For example, halogens. And here you can see an example of extraction of iodine with toluene from water. And by this mechanism, low polarity organic compounds, they will transfer from water phase to organic phase. And different substituents of inorganic nature, but that also have low polarity. And here you can see a very simple chemical equation. The main point here that we mark in what phase radionuclides occurs. Here's the aqueous phase, and always for organic phase. More complicated mechanism is called solvating mechanism. Driving force of extraction here is formation of organic soluble complex. How we can understand what molecule can act as an extractant? First of all, it's an organic soluble compound with no charge, and it contains electron donating atoms or characteristic groups. For example, such kind of groups. And by this mechanism, we can extract metal salts and acids by this equation. And some typical representatives of extractant. So, Here, for example, is tributyl phosphate. I think this is the most widespread molecule in radiochemistry because it's used for reprocessing of of spent nuclear fuel. In over the world it produces in I think dozens or even 1,000 tons per year. And another examples is a phosphinoxide called topo, and also, just for example, much part of ketones that have this group also can use as extrants. Slide. Another mechanism is cation exchange. Here, driving force is formation of organosoluble salt, and extractant is organosoluble acid. For example, 4 classes of acids is a phosphoric, phosphonic, phosphinic. The main difference between these acids is the number of oxygen that affects the oxidation state of phosphorus. And also carboxylic acids can be used as such kind of extractant. And by this mechanism, metal cations or metal salts can be extracted. Extraction equation here, I think, more complicated than the previous extraction equation. Why it's so? Because here we have exchange between protons in acid and metal cations, and during this process, the concentration of hydrogen cations go higher in aqueous phase. So it means then we can use this concentration or pH value to rule this equation. Also, another point that in organic phase there are acid dimers on non-polar solvents, and this is how it looks like the compound that present in organic phase after extraction. Slide. And also typical extractant. I think in case of cation exchange extractant, the most widespread extractant is DEHPA. It has this name. Another extractant with more sophisticated name is HEHEP. And also, when we're talking about carboxylic acids, it's very rare when single type of acid is used. It's usual that mixtures of carboxylic acids is used for extraction. Also, all of these extractants have, I think, more broad exploitation in case of just hydrometallurgy, when we need to produce some kind of stable metals, for example, cobalt, zinc, and so on. And anion exchange, here driving force is also formation organobolus sol, but here is from name we can understand the exchange of anions occurs. Extractants should contain an organic cation, for example, quaternary ammonium base, or CAB in as abbreviation, pyridinium cation and zol cation. By this mechanism, we can extract anions, metal anions such as technetium in oxidation state +7, or anion complexes, for example, nitrate lanthonide complexes. And as all of separation process, solvent extraction is a complicated process, and the main characteristic that we use to describe the behavior of solvent extraction is distribution ratio. That is a ratio between concentration of target compound in organic phase and target compound in aqueous phase. The distribution ratio is affected by different parameters. It's a concentration of competing ions, concentration of metal, depends on metal concentration, and also in the concentration of hydrogen cations, so on pH. And short case, it's a processing of targets for isolation of 2 important nuclear medicine radionuclides. For example, actinium-225 and radium-223 can be produced by irradiation of thorium target. And during this process, first step after dissolution of target is a liquid extraction to isolate of thorium micro quantities. As I say, during every irradiation of target, first step after dissolution is to remove macro quantities of matrix material. Here it's thorium. Chromatography. So in general, I think chromatography is the most wide used technique in a chemistry. With the emphasis on laboratory use, there, I think, very long list of different types of chromatography techniques. You can see some examples of it, but even there are different aggregate states, for example, gas absorption, gas liquid absorption. Every time we have the same principle. Here we also have a redistribution of components between aqueous phase or mobile phase and solid phase or stationary phase. The same as in solvent extraction. We have a redistribution between two phases, but in case when we have mobile phase and stationary phase, we can make this process dynamical by just take aqueous phase and put in through solid phase. Sure. As I say, how looks this process in a laboratory scale, and I think every chemist use this technique in his practice. And the main difference between precipitation and solvent extraction that this technique, this is multiple repetition of absorption process, and that's why this technique is in general more effective than precipitation and solvent extraction, both in case of selectivity and efficiency of isolation of radionuclides. More close look to this process. Mobile phase, it's usually aqueous phase that contain the different radionuclides. And about stationary phase, in general, it's called sorbent, and there are different types of sorbents. The first huge class is different porous solids, solid liquid films, and so on. And another maybe specific class, but it also maybe it's the most used in the chemistry, is a chromatography resin. It looks like this. And how this resin is constructed. First of all, we have inert carrier, three-dimensional framework. It's a polymer. For example, here you can see copolymer between styrene and divinylbenzene. And by some way, we put functional groups on this polymer. And after that, it looks like this. So circles here are the functional groups. You can see that they were complicated, located on the polymer. And what kind of functional groups can be used? It's that used for cation exchange. 3 types of groups. First type of groups, I think, the most used. It's a sulfur cations. They works in even in case of very strong acid solutions, and in case of phosphoric and carboxylic acid functional group, they have a limitation of usage. And also as in solvent extraction, we have ion exchanging groups that use for isolation of metals in anionic forms. And I think this makes radiochemistry chromatography specific. This is extraction chromatography. It occurs when we, as functional groups, take extractants. Here you can see different extractants for different purposes. But the idea that we put it on a polymer and after we put them, we in some kind of solvent. After that, we have slow evaporation, and it looks like a solid with a liquid film on it. And by varying of extractants, we can choose some of them that will have selectivity towards specific cation. And here case for recovery of uranium from leaching solutions under sulfuric acid leaching conditions. There sulfate uranium complexes are formed, and to remove them we should use ion exchanger that will have more stable complexes than sulfate complexes, and as such kind of cation exchanger, we can use sorbents that are based on carboxylic acid functional groups. So you can see that there's a very high selectivity towards uranium. This is completeness of removal. Uranium in the first place, and other metals in the they have a lower effectiveness of isolation. And by this technique, we can concentrate a solution from 0.5 gram per liter to 70 gram per liter concentration. And some documentation cases. Let's go back to the scheme. What we can now highlighted. Now we can highlight different separation techniques that use in this scheme. First one is precipitation. There are several studies that we use different chemicals for precipitate the radionuclides. First, here is a general precipitate of metals. And sometimes we need to use also precipitation before, for example, chromatography, or for separate of calcium and strontium, for example. Solvent extraction, I think it's there's only one place where solvent extraction is used, and used for isolation of halogens, iodine and chlorine. And chromatography, ion exchange chromatography for isolation technetium, and for in first part is for minor actinides, and here for also for ferrum and nickel. Another maybe it's more practice case. Is a program in Korea for separation of radionuclides from contaminated concentrate. And here you can see a scheme. This is general scheme, not only chemical. You can see there's some physical treatments of concentrate. And you can see there's only one place when chemical isolation occurs. Isolation of cobalt and europium, and here precipitation is used for isolation of these radionuclides. And only by precipitation we have a high decommissioning factors. And as authors of this work say, this documentation is enough to meet the requirement for radioactive wastewaters in Korea. Another case is isolation of cesium. This radionuclide have interesting chemistry from point of view of its sublimation. In a higher temperature, this radionuclide can sublimate from any matrices, and here sublimation of cesium is used for decommissioning of soils. It's a really big problem, and it was studied by different laboratories, for example, in America and also in Japan, because of Fukushima disaster. Another case is use of ion exchange resin. Here is a example from India. Is isolation of cesium from alkaline waste. They used a special synthesized organic sorbent that works by ion exchange. It was a very complicated structure. And this is stable with some kind of results. You can see that by this technique, they have treated such kind of water, and they removed, I think, a very huge amount of activity. And that's all from my lecture. Some brief conclusions. First of all, during decommissioning company, we should use separation technique for radiometric analysis and for concentrating of radionuclides from secondary waste. Main techniques, main methods of separation is precipitation, solvent extraction, chromatography, and sublimation. And in general, in both cases, in analysis of concentrating of secondary waste, we should consider combination of these techniques, of these methods, to obtain radionuclides for measurement or for concentrating it from different kind of solutions. Thank you for your attention. Do you have any questions to me? No questions. Nice. Thank you again.
Good afternoon, dear colleagues. Please start. Be ready to start. Next hour and a half, we will speak about the contamination for decommissioning needs. I am Sergey Mikheykin. I currently work in Bochvar Research Institute. It's в НИНМ, Research Institute for many directions of nuclear fuel cycles activity. And personally, our division, the decommissioning division, works for development of new technologies for all decommissioning activities. And of course, the contamination is one of the more important parts of our activity. We're developing many methods. And now we will speak about the contamination and especially about the contamination for decommissioning needs. What it is, I would like to start from definitions. What it is the contamination, decommissioning? Decommissioning is a process of shutting down of dismantling nuclear facilities, including reactors, research reactors, and other nuclear installations. So this is a last step in the development of in the development, construction, development, and operation of nuclear facilities. And this is last stage in the life cycle of nuclear facility. After then, the site of former nuclear facility will be redeveloped for new purposes or new constructions of nuclear facilities or industrial facilities or for free release. So the most important part is the last stage in the life cycle facility. And the contamination. What is the contamination? It is complete or partial removal of contamination by the deliberate physical, chemical, or biological process. So it is practically the same process that we have washing up. And especially for many ladies, it's a very interesting process. But in the case of the contamination, we have some differences with washing up of plates after dinner, for example. The first of all, it is we have a problem with old contaminations because in normal practice washing up, it is a fresh contamination, so it is not so difficult to remove it from the surface. But in the case of nuclear fuel cycles, especially, or nuclear energy facilities like NPPs, we have old contaminations. So it is very hard to desolute it or remove for any purposes. So the main differences is the problems with removing of old contaminations. Next one is differences is radioactive contaminations. So it is also very difficult for treatment. If we have a problem with very high activities, we need to use the special technologies, especially remote technologies with remote control. And it is very special cases. So it is a very big differences with washing up. But main target, it's removal of contaminations, practically the same with washing up. And the next differences is the contamination for maintenance and the contamination for decommissioning. Because if you know, the contamination, it is a very often applied techniques during the lifetime of facilities. This process needs for cleaning up of pipes, valves, for reduction of activities levels, and for many purposes. So the contamination is a normal
practice during maintenance of radioactive nuclear facilities or radioactively contaminated facilities. But in the case of operational facilities or maintenance of this facility, we have the very big problem with very strong limitations for decontamination, because during this process of decontamination, we can remove only very small thickness of surface, because all equipment should operate properly during maintenance procedure, and so we need to apply very soft methods of decontamination. But in the case of decommissioning, we don't need to use this equipment more after the contamination. So in the case of decommissioning purposes, we can use more strong reagents, more strong methods for decontamination. So it is more easy for decontaminate strong contaminations. Well, it is very important to note that decontamination is very, very big, very complicated activities, and we should remember that they are not universal technology for decontamination. It's because we have very different contaminations. We have different requirements for equipment. We have different surfaces contaminated with different kinds of radionuclides, contaminated not only with different kinds of radionuclides, but also very different chemical compositions of radionuclides. And so we should apply very different methods of decontamination for different purposes, for different facilities. And so we need to, we should know how it's possible to apply different decontamination methods for decommissioning needs. Next, very important thing that we should remember before preparation of decontamination methods, that decommissioning, it is very long procedure. First of all, decommissioning is the end of life of a nuclear facility. So we have problems with old contaminations, as I told before. And the age of these contaminations can be many tens of years, 40 years, 50 years, up to 60 years of a lifetime of nuclear facilities. And also, problem of decommissioning is a very long procedure. For example, for normal practice for nuclear power plant, it is a start to decommissioning after the 10 or 20 years after shutdown of these reactors. Is this time enough for decay of short-lived radionuclides? And so decommissioning is a process for removal and for operation with long-lived radionuclides. So we have also this problem with different radionuclides. What's the main target of decontamination? First of all, it is decreased radiation exposure for personnel. Because if you know many methods of decommissioning, it is dismantling of active components. It is handiwork, because it is possible to use the robotic systems or remote control systems, but anyway, many activities applied with handy tools, and dismantling of pipes, many infrastructure constructions can possible to made just only with handy tools. So main target of decontamination is decrease radiation exposure for safety reasons for personnel. A second target is decrease of amount of radioactive waste, you know that cost of treatment of radioactive waste is very high, and especially it's very high for high-level wastes or medium-level waste. So if the contamination can reduce activities from high-level waste to medium, or from medium-level waste to low-level waste, so we will have cheaper treatment of this radioactive waste. Or if the contamination methods can reduce activities up to free release criteria, we can apply these materials for industrial purposes. So it is more cheaper, and we can return materials to secondary application for industrial purposes. And of course, the contamination, especially in the case of the contamination of soil, it's to clean up of the site after decommissioning, because it's depending on the final status of nuclear facility. We can redirect this site for industrial application or for free release, like greenfield. So you can see many different kinds of decontamination methods. So we will speak later about this. And of course, the discussion of decontamination basis, I would like to start from the two different types of fixation of radionuclides on the surface. The first is physical deposits, physical interaction between radionuclides and surfaces. It is electrostatic polarization and London dispersion, and the strong strength of this interaction is between 442 kilojoule per mole. It is not very strong fixation of materials on the surface. And the second type is a chemical interaction. It's a chemosorption with stronger forces interaction between radioactive contamination of the surface. It is up higher than 42 kilojoule per mole. And so for removal of this kind of contaminations, we need to apply to more strong and more aggressive materials for cleaning up of this kind of contamination. What it is radioactive contaminations and radioactive deposits? If you know, practically all kinds of metals have a multi-layer structure of the surface. So it is okay, it's work. Like here, you see it is a very different levels of contaminations. For practically a few microns, but there's very different composition of chemical and physical compositions of this kind of levels. And when we will remove this layer by layer, we can reduce these contaminations. And you see this here on this picture, many levels of contaminations, many kinds of chemical and physical structure of deposits onto the surface of materials. So we can remove, if we will choose correctly different decontamination methods, we can remove this layer by layer, and we can achieve real decontamination factor for removal of these activities from the surface. Here it is just only external view of different kind of deposits on the surface. You see that it is maybe very porous materials right here. It is a layer of 100 microns layer by layer. It's this contaminations accumulated within 10 years of operation of this facility. And the pipes, here it is a pipe. And here you can see it is structure of contaminations of deposits. Like here it is very strong crystal like quartz. So it is, you understand that it is very difficult to remove this kind of contamination from surface. So we can apply very different methods of decontamination for this purposes. Here you can see very different kind of decontamination methods and how it's possible to select of the proper decontamination techniques. You can apply very different methods and very different approach to proper choose of decontamination techniques. For this purpose, many targets. It is targets for physical, chemical problems, but I would like to show you this one, cost, because it is possible to decontaminate any kind of contaminations from any kind of surface, but you can reach a very high cost. So it will be not reasonable to apply this method of decontamination, because the contamination, it is not only chemical and physical process, not engineer, not technology. It is cost of treatment of radioactive materials. So you cannot pay so high cost for this purposes. This is real life. The real application of the contamination methods can be to pay attention for these purposes. Here you see again that's the cost of each step of radioactive waste management, radiation exposure and contamination of environment, and depends on the volumes of the waste generated. It is strategy and the radioactive wastes, because you know that the contamination is just only one of the different methods of treatment of radioactive waste. And we will speak later about the contamination of in situ and the contamination after dismantling of facilities. So, like all radioactive waste management principles, all these principles can apply and for the contamination needs. One of the most problem of the contamination methods and the main target of the contamination is keep generation of radioactive waste as low as possible, because it is cost of radioactive waste, and we can clean any surfaces, but we can in this case we can produce a very big amount of secondary radioactive waste, so it will be not reasonable because it is very high cost and very different to treat very aggressive or very big amount of aggressive radioactive waste, secondary radioactive waste. One main idea for understanding how effective the contamination method, it is the contamination factor. It is not exactly clear for understanding of this process, because the contamination factor can be very different. But for understanding for possibilities of comparison of different decontamination methods, we need to set up some criteria, and the key criteria is the contamination factor. It is a ratio of initial activities, high activities, to final activities after decontamination. The contamination factor can be 1, 2, 3, up to few thousands of, depends on, especially it is depends on initial activities, because it is very very easier to decontaminate with high efficiency of high activities, but it's very difficult to clean for secondary, for few steps, to clean low level of activity, because it's low level activities usually very strong fix onto the surface. Here it is, you can see a list of different decontamination methods and the decontamination techniques. In red, it is more useful methods. It's in accordance with EA technical report series publication. So you see it is that we have a lot of different decontamination methods, and here we will speak about these methods in detail. And traditionally, we start from chemicals. It is chemical reagents normally applied into the water solution, in the water solutions, for the contamination of different surfaces, different kinds of contamination. And normally it supply aggressive chemicals like acids or bases for different purposes of treatment of our surfaces. The first of all, if we remember, this multi-layer of deposits on the surface, we can open these activities, open these contaminations for reagents, and then treat it with strong acids, strong or organic acids, inorganic or organic acids, for the cleaning up of surface, for treatment of chemically of these surfaces. Chemicals, it's very applied very widely for different kinds of decontamination, and it is one of the more main advantages of these methods. It's possible to find proper decontamination techniques by chemicals practically for any kind of contaminations. It's really very useful and very good methods, but it's and with very high decontamination factors. It's possible to treat different kinds of metals, plastics, any kinds of materials practically, with very complicated geometry of the surfaces. But one of the main disadvantages of this methods, it's very high amount of secondary radioactive waste, very aggressive chemicals. So because to treat this kind of secondary waste is very difficult, and so it is a very big disadvantage of this methods. But this methods traditionally used up to now, and we see it, and it is very effective. For this purposes, it's possible to use very different approaches, so low high oxidation, dissolution methods. So it is very wide choice of these techniques for this purposes. The main idea is dissolute of the deposits from different surfaces. It's very important to note that chemicals can apply not only by one step. It's possible to treat step by step with different chemicals. For example, here you see possibilities to apply the three steps of treatment as by alkali, acids, and acids, organic and inorganic acids. And so a combination of different methods for stainless steel can reach the contamination factor up to 2000. This is very good decontamination factor. Here it is a list of different decontamination compositions, and depending on materials what you need to treat. I'm sorry, it's carbon steel, stainless steel. So you can apply very different methods, but it's also important to note that all chemicals are good operated with high temperature. The normal temperature of this process are starting from 80 up to 95 centigrade. So it is not only difficult for treatment of secondary radioactive waste, but also it's problem of cleaning up of secondary aerosols, contaminated aerosols, and also it is very big, very high energy consumption for this process. So you see it's different decontamination methods. I think you will have copy of this presentation, so you will choose different methods if you will have this problem. And it is also important to compare the contamination before or after dismantling. Because if we have a problem of the contamination before dismantling, we have the problem with big size equipment which operated on the, or located on the big rooms, and we should apply different decontamination methods. Or the contamination after dismantling. After dismantling, we can cut this equipment for smaller parts, and we can organize special facilities, the contamination facilities, and practically it should be industrial facilities, small industrial facilities for decontaminate of different materials. Before dismantling, we can decontaminate, like here you see for NPPs process. It has methods of decontamination of steam generators, because it's very difficult to cut it for dismantle for smaller parts, and normally, but it's possible to use, of course, different methods for cutting of this steam generators. But normal practice is the contamination of mainly contaminated loops of reactors before dismantling in situ. For this purposes, it's possible to use very aggressive chemicals. Here you see the list of this. I'm sorry. A list of chemicals and regimes, and you see that it is possible to use very high temperature, high pressure, and flow of the streams. It's practically few hundreds of cubic meters of reagents for this cleaning up. But as a result of this kind of decontamination, you will clean this first loop of reactors, and you can cut it without this very complicated robotic systems if you will apply these methods of decontamination. So it is one of the example of the contamination methods. It is the contamination of reactors units 3 and 4 of Kozloduy nuclear power plants. It's Bulgaria. It will apply low alkaline solution and temperature of 135 centigrade. It was using full 2 steps of dissolves of corrosion layer as different chemicals, and the contamination factors reached up to 1 to 28. It was very good decontamination factor, and it was recover very high activity from this first loop of reactors. So it is chemical process of chemical decontamination. So it is different approach for decontamination. I see we have time. And second kind of decontamination is forms, application of forms. These methods practically is similar with chemical decontamination because it's also operated in the water media, and it's possible to apply chemical reagents. But if we will have a problem with very high level or high amounts of secondary water wastes in the case of chemical reagents, but for foam, we will apply low amounts of less amounts of water, and because application of surfactants is possible to organize of bubbles of material, and these bubbles can reach the all surface, even of very complicated surface of metals, and in this case, all reagents will be reach also surface of contaminated surfaces. But during the process of life of foam, it will be operated onto the surface. So we have this practically the same approach. All chemical reactions are in the water media, but then after the lifetime of foam, foam will collapse, and water will be moved to the and we can remove this water from the surface with different methods. Practically, it's by vacuum cleaning methods, or with some different approach. In this case, we have a combination of chemical decontamination and reduction of secondary radioactive waste. But negative thing of here is impossibilities to apply very strong chemicals for preparation of foams, because in the case of very high concentration and very strong activities of chemicals, this foam can be collapsed. So we can keep some balance between needs of strong reagents and the possibilities to life of this foam. So this method applied widely for very big volumes, very big size of equipment, for different orientation of the surface. So advantage of this method is a small amount of chemicals and secondary wastes. And one of the main disadvantages is a limited lifetime of foam. And because it's collapsed, and we should treat it again or complete these methods before the final process. Next kind of chemical reagents methods is the electrochemical decontamination or electrochemical polishing of process. This method is anode dissolution with transition of contamination in solution after treatment of the surface. And, usually it's applied, this method applied into the chemical solution of phosphoric acid. So the disadvantage of this method is a very strong composition of secondary radioactive waste because it's electrochemical dissolution. But advantage of this method, it's activated of the activated of the chemicals with electrical current, and you see the solution of upper layer of the surface up to starting from hundreds of microns up to millimeters of the surface. So this method is very useful. It's possible to apply not only phosphoric acid but also sulfuric acid. It's possible to apply different oxidation methods also. It's possible to combine different decontamination reagents and electrical current. Density of electrical current is usually up to 1 ampere per square centimeters. It is possible to use different kind of application of these methods. It's possible to use this bath like here. So it is very big amount of secondary radioactive waste here, aggressive radioactive waste, or application of external electrodes. It's also developed in our institute. So it's possible to use anode dissolution, like we can switch this electric current to the corpus, to the side of this contaminated glow box, and after diluted with chemicals using this external electrode like here. So it was applied very good efficiency, but this method is not good for complicated geometry. Also, of course, because it is very easy to apply of flat surface. Like here you see this dissolution of surface, anode dissolution of surface into the bath, like here, or application of external electrode where we have this bath is just only here. There's a thin layer between contaminated surface and this external electrode. So, but chemical decontamination are in this here in this thin layer of reagents. The next method is ultrasonic decontamination. It is combination of water solutions. It's possible to apply also chemicals for this purposes. But a very important part is combination of chemical treatment of surfaces and cavitation process. Because during, as a result of interaction of ultrasonic into the surface, it has created bubbles, small bubbles on the surface, which have a very short time life. And then after collapse of these bubbles, we have process of cavitation. And this during this cavitation process, surfaces treated with very quick impulse of then mechanical activation, and so all these surfaces treated like mechanical crust of this contaminations. So this method is very useful for different purposes. It's possible to apply in the wide of range of 20 or 50 kilohertz. As current of this ultrasonic, and it's possible to apply the two or small tanks or some small units, or even for big tanks like here up to 20 cubic meters of volume. Of course, it is not radioactively contaminated methods, not radioactively contaminations. It is oil contaminations. It is so, but it's possible to treat. It's a very different purpose and very different approaches. So, next block of decontamination methods is the application of polymeric films or polymeric strippable coatings. The advantage of this method is during this process, activities on contaminations encapsulated into the structure of polymeric films and can remove from the surface jointly with these polymers. Advantage of this method, it's application of chemicals from water solution. So it's possible to use also the different chemicals, but not very aggressive. But also we can apply organic or mineral acids or alkali. And then these polymeric films, mainly based on polyvinyl alcohol, this polymeric solution applied onto the surface and then waiting for a few hours for drying up of this surface. And then after formation of this polymeric films, it can be removed from the surface. So in this case, the first step of decontamination also are in the water solution. So it's more applicable for chemical dissolution of surfaces. So in this case, you see, like here, after treatment of the surface contaminations, here you see oxide layer. It is a real treatment of alpha contaminated stairs in our institution. These polymeric films accumulate these contaminations, and here it's impossible to remove polymeric films with this contaminations. And here you can see amount of secondary radioactive waste is very small. So it is a very small amount radioactive waste created from the very big glove box. And it's very important that it is not liquid radioactive waste, it is solid radioactive waste. So normally many nuclear facilities or decontaminated facilities has not their own system of treatment of secondary radioactive waste, liquid radioactive waste. But it is very easy to accumulate solid radioactive waste. And so it's more easy to treat solid secondary radioactive waste. So it is a demonstration of this process. This polymers includes also polyvinyl alcohol, additives, different additives. It's possible to apply the inorganic or organic acids. It's possible to apply complexons for the contamination purposes, and of course plasticizer like glycerol for better mechanical stability of these polymeric films. So you see there's different decontamination factors for this purposes. So concrete and bricks, of course, it's possible to treat. Like here you see application of polymeric films for very different materials. It's possible to apply it and remove from different kinds of surfaces. But of course, the contamination factor for porous materials like concrete or bricks, it's very low. And it is not big reasons to remove, but this method, it's very good to apply for fresh contaminations, for fresh, not fixative contaminations. And this methods we applied very widely for Chernobyl nuclear power plant decontamination area, for the within few first months after the accident. So this methodology is very good and applied very widely for different purposes. Next generation of polymeric strippable coatings is decontamination gels. It is practically the same, similar with polymeric films, but the gels kind of very good possibilities to destroy after drying up, because one of the main disadvantages of polymeric films is very big difficulties to remove very thin polymeric films, because it has not very strong mechanical strength. So we can remove very softly from the surface. And it is not possible to remove from the very complicated surfaces. But in the case of polymeric gels, it can destroy itself after drying up, and it's possible to remove just only applying of vacuum cleaner after this treatment. So it is a very good continuation of the development of polymeric materials for decontaminations. The next method, it is not chemical methods, of course. It is a laser cleaning, laser decontamination. Very important that in the energy of laser beam, it's absorbed by surface, and surface immediately heated to very high temperatures, up to plasma temperatures, and then also is very quick cool it up. And so during the process of I'm sorry for forget this term. So we have a different size reduction within temperature for different materials and for different parts of this material. So this heated materials has a high size dimension, and then the surface cracked, like here you see, and can remove from the surface of materials. And so for this this treatment, it's possible to treat very corrosive layers of metals, like here, or concrete, like in the previous photo. This method now widely applied for different purposes, because development of laser technologies is very quick. It's possible to apply different kinds of laser beams, different kinds of laser installations. Main parameters you can see here on this picture, in this slide, and so this is one of the more interesting methods of decontamination. It's very good for application, because we have a very small amount of secondary waste, just only cracked materials. But the problem is purification of secondary waste, aerosols, because during this process we raise a lot of radioactive aerosols. Next group of decontamination methods, it's mechanical decontamination. It is a very simple method of decontamination. You see, it's possible to apply it like here, just only treated surface and remove contamination from this surface. But of course, handling method, it is not a good idea for radioactively contamination. So widely applied very different methods, very different techniques. But anyway, we can, if we will destroy surface like here, we can create a lot of secondary waste in the form of radioactive aerosols. So main idea, it is possible to treat any surfaces with mechanically, but the main idea is we need to remove secondary aerosols immediately after creation of this aerosols. So for this purposes, developed this technology and special installations which can remove these aerosols from the surface by vacuum cleaning methods and then treat it by cyclones, filtration, and accumulate secondary wastes to the standard drum for future treatment of radioactive waste. So one of these methods is needle scaling surface. It is very interesting because each needle treated with own trajectory. And so we can treat it as a complicated surface with complicated geometry. And it's very efficiently, and like here you see using of the different method, different form of needs we can apply. We can treat different kind of material surfaces. Scabbling, practically the same methods, but with application of special beads from the very strong alloys, tungsten alloys usually. And here you can apply this robotic system, like here, for cleaning up of floors and vacuum cleaning of aerosols from this surface of floors. And here you see the same system, cyclone filters for cleaning up of secondary aerosols. This methods very widely applied for concrete surfaces, both like shaving, for example. It is possible to apply also for floors, for walls, for different geometry and different location of the surface. Methods is practically the same. Concrete shaving applies this different tools like here, for very soft cleaning of contaminated surface. Both concrete bricks, painted or not painted, it's no difference because it is a mechanical treatment of surface. Jet decontamination. For this purposes, it's possible to apply water jet or application of abrasives like here. Main idea of methods is transfer of energy from kinetic energy of the small parts to surface, and during this process of treatment, surface is destroyed and remove contamination from the surface. If you remember the first photos of deposits, it's possible to treat these deposits with different methods of abrasives. It's possible to apply very wide list of abrasives, minerals, steel pellets, ceramics, plastic pellets, or carbon dioxide or dry ice, like here. For dry ice, it's possible to combine methodology of abrasive cleaning, and practically the same methods like we use for decontamination with laser. But during the laser treatment of surface, we can heat surface. But in this case, we also very quick cooling up surface, and also surface this contamination destroys as a very big differences in the temperature of inner layer of surface, and the treatment of carbon or dry ice. So we have an effect of thermal shock, and in this case, surface destroyed, and we can remove it's from contaminate. We can remove contaminations from surface. This method is very good from the point of view of minimization of secondary waste, because we have practically no contaminated secondary waste like abrasives, because dry ice is evaporated immediately. But in this case, we have very big problems for treatment of gaseous secondary waste, because dry ice evaporated, and we can apply very strong method for decontamination, for treatment of secondary gaseous radioactive waste. Water jet. It is the simplest method of jet technologies. It's also impossible to apply for very complicated surfaces, very complicated geometry of cell surfaces. It's possible to apply different pressure of water jet, starting from 50 bars and up to 700 bars. It's possible to apply the very good thing for this methods is a very low amount of water jet, because as a result we'll have very small amount of secondary radioactive waste as water, but also during this treatment we will create a big amount of secondary aerosols. So this method should apply in the special boxes, like here you see, like in this picture. And this method is well operated for the contamination of different kinds of surfaces. It's very special methods of the contamination of copper cables. You know that the problem of cables, contaminated cables, is very big problem for different facilities, because communication in any way, we have a lot of this cables. It's very easy to decontaminate, because in this case of cables, we have contaminations just only on the polymeric materials contaminated. So we will destroy the surface. We will destroy these cables for small particles, and then separated. It comes through cutters, then separated the dust separator. So it's separation by weight, as polymers has not very high mass. So then air separation table, insulation, it's one thing, copper, clean copper, because it's practically not contaminated, is accumulated in the different parts. So it is very easy methods, very good applied. Before, all my presentation was about surface contaminations, but in many cases, especially in the case of reactor core, we have problem of with activated materials. We cannot apply any decontamination methods for decontamination of activated materials, because activated radionuclides here, in this case, radionuclides are into the deep of these materials, so we cannot remove it with application of surface decontamination methods. Only method for decontamination of activated materials, it is decontamination by melting. For this purpose, it's possible to use different kind of furnace, but normally and more suitable for decontamination is melting with in induction melting. In this case, application of special flux, we can remove the contamination from the surface of these metals and from the inside of these metals, like activated materials. We can remove to flux with special flux. And one of way for the contamination. Second way is for volatile radionuclides like cesium, for example. It is transmission of cesium to flux or to volatile with off-gas treatment system. So in this case, we can decontaminate very wide kind of materials like activated materials or contaminated materials. All these metals comes, it is rare earth elements, sorry. In this case, we have clean ingot after melting and contaminated slag, which can be accumulated to treatment as secondary radioactive waste. So this method is very widely applied. We have it is combination for application of this method. It's very important to apply properly composition of flux for different kinds of, for stainless steel, for carbon steel, for zirconium alloys. It's possible to decontaminate with different kinds of contaminations. We applied this methods, this kind of flux for the contamination of metals from uranium and plutonium for Russian nuclear facilities. But really it is applied, this is for low-level contaminated materials. This technology applied widely for Ecomet S company, Russian company. And you see it's ingots, it's very complicated geometry like here, but this ingots, it's very clean. Good. Here you see a list of different facilities. You see it's separated very old facilities, starting from 90s or 80s of the 20th century. So it is very good technology operated widely for. It is important. It is possible to apply these metals for free release if we have clean materials, or it's possible for different purpose is application for preparation of cask for radioactive waste. Also, it's possible to apply these metals for recycling. And last part of my presentation is the contamination of soils. It's very important to say that during the normal operation of facilities, nuclear facilities, it's important. It is impossible to contaminate soils because normally contamination of the soils, it's impossible. It is normal operation. But in the case of leakage or accidents, it's possible to meet this contamination. One of the first time we meet this problem in Ural in 1957 after the accident of the Mayak facility, and last were very big contaminations happened in Fukushima site in 2011. So you see, it's dependent on the time. It's possible to contaminate surfaces, but in this case, it's possible. It is important to know that contamination accumulated to the top layer of soil, and the penetration of radionuclides into the soils depends on the time after accident and the activity of atmospheric deposits. Because immediately after accident, it's possible to remove just only few 1, 2, or 3 centimeters of soil, and in this case, we will have the small amount of secondary radioactive waste. But within the first year, depending on the kind of soil, penetration can reach 5 or 10 centimeters. So for treatment for cleaning of surface, it should be removed more materials and more in treatment of the it's need to treat the highest amount of secondary waste. The simplest way for decontamination is removal of topsoil. So like here you see all photos are after Fukushima accident. It's possible to remove mechanically by any methods. Handly, with hydraulic machines, any methods for remove and to collect of these materials to storage facilities. The second method for the contamination of soil is deep pluging. This method is developed after accident of Ural accident in 1957, and main purpose of this methods, it is transfer of highest level of contamination from the upper level of soil to the deep level of soil. It is not decontamination exactly, but in this case, it's possible to clean surface because the surface can be very dangerous from the point of view of transfer of secondary contamination from the surface. So if you will store the surface to the deep layer up to 30 centimeters, we can keep these radionuclides inside surface for few 10 years. So it's maybe enough for decay of short-lived radionuclides and not try and to protect transfer of this radionuclides from the surface for contamination of new areas. So this methods of decontamination is also widely applied, not only in Ural, Chernobyl, and also in Fukushima site. You see like in here, these 4 photos. And then it's possible to separate methods for 2 big trees. The first of all, it's radiometric separation methods. So you know that it's possible to organize the special conveyor for which will includes this detector. So you will treat this contaminated surface, contaminated soils, and then put it to the conveyor, where it will be, which is this conveyor includes detector, which will be measure these parts. It's very important to have the one geometry for this layer with one depth of the soil And this detector can be programmed for critical criteria. And when we will have higher level of activity, then this detector can apply. This conveyor will be switched off to the contaminated parts, and the contaminated materials comes to the container for radioactive waste. If we will have less contamination than criteria for this segregation, these materials will be clean and will be accumulated like green materials. Initially, the first time this system applied for with the name of segmented gate system was developed in the United States and operated in Albuquerque for the decontamination of territory of Sandia National Laboratory. It was developed a few thousand of cubic meters of contaminated soils with efficiency of 99%. So just only 1% of soil was stored like radioactive waste. Now, I'm sorry. Now this methodology applied with new methods and new detectors. It's name of premise system and applied now for Angarsk combine in the Russian Federation, and now also operated for the contamination of sandy soils, like here in Sandia, with also the same efficiency. Next group of methods for the contamination of soil is soil washing process. It is very important that, like here you see, it was established after Chernobyl accident that main specific activity accumulated the thin parts of soils. It is normally for different kinds of soils. So if we will able to remove these very thin particles of soil from contaminated soils, we will decontaminate the surface. So you see, like here, it's very different methods. Main activity accumulated in the fine particles of soil. Especially these methods are very effective for sandy soils, because in this case, very easy to decontaminate, for destroy this contamination from the sandy surface. And this this facility was constructed in 2003 for the contamination of 10,000 cubic meters of sandy soils of Kurchatov Research Institution in Moscow. And this principle was very easy. This installation destroyed small particles, is clean it up from this clean sandy soil, removed this big clean debris. This debris were also clean. It just only very small amount of fine decontamination of fine contaminated materials was collected to the containers for radioactive waste. And so the contamination factors for this installation initially was developed, reached as 4, but finally after the very smart modernization of this installation, it was reached up 5. So this installation treated more than 10,000 of cubic meters of soils and operated few years. So it is external view of this installation. So it's now this practically this kind of installation also operated in our institution with very high efficiency. But this installation can operate this methods of decontamination very good for sandy soils, but not applied for any kinds of soils, because there's a different distribution of small particles in the different kind of soils. And the last of methods of decontamination is chemical extraction. It's practically the same method of treatment like washing of soils, but in this case I applied different chemicals, mainly acids. Disadvantage of the advantage of this method is high the level of decontamination factor, but disadvantage is very serious, because in this case treatment of treated soils really are not soil. It's industrial waste, because it's treated with strong chemicals and the soil structure destroyed finally. And so it's impossible to use for returning of this soil to the initial site. So we need to treat it like industrial waste. So for road construction, for example. So, and of course, it's a big consumption of reagents for big amounts of treated soils. But this methods also operated and also very efficiently. And last method, sorry, it's not last. Last method is feed extraction. Feed extraction, it is the application of plants for development, for removal of dissoluted radionuclides from the surface, from the topsoils. This method is applied for uranium, for removal of uranium, strontium, and cesium. Main idea that is transfer of soluble radionuclides from topsoils to plant. Then you can collect this plant from the surface, and storage is like secondary radioactive waste. But main idea for this methods and the main disadvantage is very small ratio for distribution of radionuclides to plant. So for real cleaning of surface, you need to apply the many seasons of treatment of this surface. So this method is possible to use, but for real application, I think, it's my personal view, it's maybe not reasonable method for decontamination. So it is finished. If you have some questions, please.
Sir, I have a question. You talked about the different methods of decontamination, and all these methods involve removal of the deposits. Is there a way that, instead of removing the deposit, we can just cover the deposit by painting or surface coating? That way, the criteria for decontamination is also met, and then there is no secondary risk.
Sorry. Repeat, please. I'm sorry.
In all the decontamination methods that you talk,
Yes.
there was a removal of the deposit.
Yes.
Isn't there a possible way wherein we can do surface coating to reduce secondary waste generated and achieve the decontamination?
We should remove the all deposits.
Is it possible?
Yes.
Just surface coating, like painting, for example, or coating with lead.
Anyway, we should remove the all deposits from the surface. very often it's possible to contaminate not only deposits but also thin layer of metals. So ideal system, we should remove deposits and very thin upper layer of metal. So we can apply different methods for this process. Please. Radiometrical decontamination. Yes, impossible combine. Yes, I discuss my main kinds of methods of decontamination, but normally it's possible to combine different methods of decontamination. Of course, yes, it's possible. For example, for decontamination of soil, we applied the soil washing process, but then we combined it with ultrasonic application, and the efficiency was so high there, of course. Yes.
Its appearance and presence is felt for a long period.
It depends on chemical abilities of this radionuclides, because you know that radionuclides are not independently. It's really in real life and in ecosystems, radionuclides combine with other chemical composites. And so it's set up, created this good interaction with different materials. And so how we can remove it from the surface? Not exactly, because we have not clean plutonium or uranium in ecosystems. We have a combination of different chemical composition of uranium with materials. So we need to remove these materials from surface. That's my idea.
Your last slide.
Said
plant one special kind of wood that it will remove or lower radiation around
well, plant is good, maybe a good idea because it's possible to accumulate. Plant can accumulate radionuclides, but then you, for better results, you should remove these plants every year, maybe a few times per year from the surface. Anyway, in any case, these plants accumulated, but only a small amount, small part of activities, because it's a life cycle of plant and it is a consumption of this radion. It is not a radion class. It's like micro parts. Yes. So, and my point of view is not good idea to transfer those fixed radionuclides, because normally radionuclides very quick fix it onto the surface by mechanical or chemical interaction. And then we will transfer it again to the water-soluble form to the grass, to the plants. And then we can collect all this grass or plants and treat it again for like treatment of radioactive waste. So for me, it's too complicated approach. please. Mhm. I'm sorry, I'm not biologist. I don't know the names. Yes, I know just only that it is different plants, very special plants for extractions, not widely planted grass, for example. But I not remember the name of this plants. Sorry. Yeah. No, it's impossible to remove radionuclides directly from soil to plant. So I don't know. I'm sorry. Mm. Which method? Feed extraction. No, I know that after Chernobyl, it was a few research works in Ukraine and Belarus, I think. It was, yes, it's a low period of vegetation, very small ratio of distribution between soil and piles. So you see like this here in this picture. So for reach of desired reduction factor, you need to have annual removal % per year. It is, well, from my point of view, it's not industrial application. No, not perspectives from industrial, but maybe for Greta Thunberg it's good. I don't know.
Can grow on alternative territory.
Yes, and of course, it's for big territories. Yes. Yeah. That please.
Which are converted to decontaminate this laser.
It depends on, you remember the first slides, it's very big choice of methods. Yeah, it's good methods. But application not ready for very big perspectives now. Yes.
I think the laser was when the person gets to
Yes.
laser expensive or
No expensive. Now it's not expensive. Now we have a lot of cheap lasers for industrial application. It's not only for nuclear applications, for industrial applications, possible to clean up the surface. Yeah, yes. So it is not expensive now. Yes, it was very expensive and difficult to apply when we started this works into the end of 20th century. Yes, it was big lasers, thin beam. It's very big problem with focus of this beam. But now it's more easy. For metallic and concrete also.
Complex areas.
Yes, yes. For flat surfaces, it's preferred now. Aerosols. Aerosols and application for flat surfaces, not for complicated geometry. But maybe a few years later, it will be also solve this problem. I don't know. So, no questions. Thank you for your attention.
No, sì, prima por momentos nunca había que en San Gabriel de noche el servicio meteorológico.
Dear colleagues, I'm ready to continue. As I mentioned in my previous lecture, this related to the dismantling equipment and building structures of nuclear fuel cycle facilities, and related to practical works on examples of two performed projects, decommissioning projects. I will tell about features, specific features of dismantling main process equipment. Show the difference between approaches to dismantling and choice of methods, because two workshops is the same, but methods are different. Now, I want to tell you about decommissioning uranium isotope separation production workshop building number 804, and about main stages of this project. Now it's completed. The first stage was preparation works, creation infrastructure, creation physical protection system, radioactive waste recycling areas, waste accumulation and management areas, and so on. Then confirming engineering and radiation survey of building structures, dismantling the utility equipment and networks, then dismantling diffusion systems and interblock pipe communications, dismantling of building structures, bringing the territory into safe condition with rehabilitation, and backfilling the excavation with inert material. Here you can see brief information about the numbers. In 2020, the work package envisaged by the project was fully implemented. And here you can see the main numerical indicators of the completed project. As you can see, the project is a large scale. Let me remind it that it is about 1 kilometer length. Nevertheless, the main stage was implemented in less than 4 years, and more than 5 specialized organizations were involved in the main stage of this project. Dismantling process equipment. Detailed information about process equipment dismantling. Inside of the building, there are 15 blocks of diffusion machines were subject to dismantling. It means in each block there are 22 machines, so total 330 machines, total weight of metal over 5,000 tons. Each machine, each unit includes the following assemblies. Process tank with a filter cell cartridge installed. Lower compressor for injecting working gas. Into process tank, upper compressor for taking the light fraction of the working gas and feeding into next unit, and upper and lower cooler for cooler to cool down the working gas after decompressing by compressors. These operations were performed for preparation for dismantling. And dismantling of gas diffusion equipment is performed using a semi-knocked down disassembly method. Dismantling is carried out on a top to the bottom sequence. Main methods were plasma cutting and hand cutting tools. After this, preparation works. Dismantling assemblies of diffusion machines are subjected to radiation monitoring. Radionuclide contaminated assemblies are covered with PVC compound and placed in intermediate sites separately, according to the results of the preliminary categorization and the intended recycling methods. All dismantling assemblies are craned to a special intermediate storage area lined with polyethylene film to prevent contamination of the area due to falling of process deposits from the internal surface of the equipment. Why plasma? No. As I mentioned, the main method of dismantling was plasma cutting. The technology of plasma cutting of metal is based on creating an effect by means of an electric discharge in gaseous medium, and is suitable for processing metals up to 50 millimeters thick. Plasma systems also are considered to be more versatile, high speed and high quality cutting methods. Cuts made with a plasma cutter always have less draws, less bending, and smaller hot area. Can be used to cut any metal, includes mild steel, aluminum, stainless steel, copper, and many others. Oxy cutting more dangerous, but if you are worked with thick over than 50 millimeters, it is more suitable for such works. And oxy fuel cutting is used only for mild steel. during this project, we use plasma. And now at the moment, the decommissioning of building 802, it is the same production, complete analog of 804. Now it's continuous. About 50% of work provided in the project documentation is completed. The building is freed from equipment, building structures deactivated. Part of building, third part of building dismantled, and solid radioactive waste generated during the decommissioning, as it's brought to the acceptance criteria, is compacted in special safe containers and transferred for final disposal to national operator. The decommissioning of building 802 planned to be completed in 2025. Complex for handling metal waste contaminated with radioactive substances has been created in Angarsk, as I mentioned, the decommissioning competency center, and all generated waste is recycled there. The following technologies for handling metal waste contaminated with radioactive substances are used: fragmentation workshop with special equipment that allows cutting large diameters pipes, installation of abrasive blasting, which deactivates fragments of equipment by removing a layer of oxides and material from the surface. Also, we use liquid decontamination. It is when metal equipment are placed in a special chemical substance. Cryoblasting, it is an analog of sandblasting, but it uses dry ice under the pressure instead of sand. Pyrometallurgical processing, and so on. In contrast of decommissioning of building 804, this project started using a mobile laser complex, which was created of the framework of 12 project. And in the course of approbation works on fragmentation of diffusion machines without preliminary disassembly were performed. It should be noted that now, at the moment, approbation still in progress. What are the advantages of laser complex, laser cutting? It allows to carry out the process of fragmentation and dismantling of gas diffusion machines at a considerable distance. Also, it allows do it in cramped conditions and allows for, to do fragmentation without disassembly and extraction filter elements. What else? Two same productions, but methods are different. We develop new methods, and now quite approbation of laser cutting that we will implement in our next projects. And of course, it depends on cost, condition, safety, and other factors which it consists. Thank you. It's all about dismantling equipment on examples. And наверное, паузу сделать. Now we will continue with dismantling of building structures. Slide number 9, I think, 8 or 9. Okay, here we also talked about dismantling of building structures on two performed facility, performed decommissioning project. Already familiar to you, 804, the same 802, and object facility in Moscow, installation U5 that were completed in 2021, previous year. Next slide. On this slide, there are characteristics of construction, building constructions of 804 and 802, and stages of dismantling building structures. The sequence of work on the liquidation of the building are visual inspection, development of measures for instrumental inspection of building structures of the building, and as I mentioned in my previous lecture, there were there are different structure conditions, and inspection were in about 804. Inspection shows that the result of this inspection shows that building structure were in critical conditions. So then we carry out instrumental inspection of the building structure, and then strengthening of the building with indication of the conditions for the safe performance of dismantling. Led to significant increase of cost, of time of work, because this stage weren't in our design documentation. Next slide, please. Then we provide mechanical decontamination of building structure, collection of waste contaminated with radionuclides, radiation monitoring, then dismantling of building structure from top to bottom, transfer all metal structures which are not contaminated with radionuclides to the operating organization for sale, and processing of reinforced concrete building structures not contaminated with radionuclides at the crushing and sorting complex. Formation of secondary crushed stone for backfilling of the pit. This work carried out in 3 stages, sequentially for each third of the building. Removal of the roof, dismantling floor slabs, dismantling of external and external and internal walls, metal trusses and columns, and the floor covering be removed. At the transition to the next stage, an awning shelter was installed along the entire height from the side of the demolished part of the building to prevent the possible release of radionuclides along with construction dust. In accordance with adopted design decisions, the foundations of the building weren't removed. Stay here. Next slide. And this is specific features of what that can be distinguished here. First, due to the fact, according to the results of survey, the building was in a partially emergency condition. For the safe performance of work, it was necessary to strengthen building construction. It significantly increased on cost and time of work. The dismantling of the building was carried out in stages. After the dismantling of equipment and system in each third part of the building, this part was cut off and it was dismantled. This made it possible to carry out various work while 1/3 of the building is being demolished. Equipment is being dismantled in other part of it. And the third feature, construction waste not contaminated with radionuclides was processed at sorting and then at crushing complex and used for backfilling the pit. Okay, and next slide. And now we look at definitely another project in Moscow. Works on the liquidation of the building unit at NINM was carried out in a completely different way. The building installation was put into operation in 1945, and based on the result of the radiation examination facility, it was found that indoor pollution it caused by plutonium and local sources of beta gamma radiation with dose rate up to 150 microsievert. In accordance with the design documentation, a decision was made to decommission the U5 under the liquidation option. I mentioned it is Moscow, so the territory of the installation is surrounded on all sides by dense residential development. Radioactive materials which are present in significant amounts in premises, equipment, and communications pose a potential hazard to personal environment and public. Subsequently, part of the equipment was used of this installation was used to collect, store, and extract plutonium from liquid or radioactive waste. As a result of the operation of U5, number of technological premises and equipment were heavily polluted and were mothballed during the reconstruction of the building in the 60s. The building contains 2 shafts with extraction columns with hot cells. By the time the work began, most of the premises were contaminated with radioactive substances of various physical and chemical composition. Part of them is corroded. The condition of the building installation can be assessed as unsatisfactory also. Stage of works. Next slide. During the work at the second stage, I mean removal of radioactive waste from building structures. The following deviations from the design solutions were identified. After the contamination of building structures were carried out and indicating the presence of multiple local radiation anomalies on the first floor and basement of the installation. At the same time, the continuation of decontamination work was impossible due to the risk of violation of the bearing capacity and collapse of the building structures of the installation. Due to the presence of contamination building structures, dismantling of the first floor and basement of U5, according to design solution, posed the risk of spreading radioactive substances into the environment, especially taking into account the location of installation. To ensure safety during disassembly and dismantling of the installation, it was proposed to perform a number of compensatory engineering and technical measures not provided for by the project. It was decided to carry out dismantling works in 2 stages. Dismantle the roof, 4th, 3rd, 2nd floor, up to the overlap at the 1st floor. And on the basis of the 1st floor, perform work on the creation of protective shelter. With several engineering systems, such as ventilation, radiation control system, and another. Thus, to perform dismantling the contractor, together with the designer, prepared a technical solution for the dismantling of the unit and developed the corresponding project for the production of work. Works in accordance with this technical solution were successfully implemented, and decommissioning project was completed on time, safety, and with proper quality. What features? Next slide. Inability to fully complete decontamination work due to the risk of collapse of building structures. Need to design an additional safety barrier on the base of 1st floor and basement, and that the work was carried out in cramped condition inside of this bunker. We use remote robotic tools as shown in previous slide. That's all. Thank you for your attention.
This situation, was the project completed or was it halted?
Help me, please. My English is not perfect. I do not understand at all. Or I not confident that I understand it right. Maybe somebody will repeat it in Russian, and I will try to answer in English. Так, мне Андрей обещал помочь с ответами на вопросы. It's fully complete, successfully completed on time in 2021. Невозможно завершить дезактивацию. Okay, I will try to answer. Because of this, all decontamination works was under inside of this bunker, which covered installation on the base of 1st floor. And then we dismantled foundations and completed this project. Я справился, мне кажется. Не, пока все. Пока вопросов больше нет. Потому что не сразу поняли все.
Вопрос?
Ну, конечно. Thank you very much.
Hello, good afternoon from Vienna. Can you hear me?
So what the number of the page we need to show?
Let's go ahead and I will tell you. We can agree on something.
Okay.
So next one.
So, dear colleagues, please take your seats. Thank you. Yeah, we can start. Thank you very much.
Thank you. Andre, I think that you can go probably to slide number 8.
Uh-huh.
Let's see what was there. Next one. Next one. Okay, we can start from here. Very good. Well, first of all, once again, apology for yesterday. This evacuation exercise was totally out of my control. It is for actually selected buildings and all staff to go by walk, you know, in my case, minus 29 floors down to ground floor. And it is not known in advance. It's usually happened in August in some time. So yes, it happened yesterday. Sorry for this. Well, I mentioned that one of the part of our activities is development of the technical reports and safety standards. So here you can see selected examples of an IEA Nuclear Energy Series reports and tech docs on various aspects of decommissioning. I selected mainly the new reports. Everything is accessible through the agency website. And those covers technical as well as non-technical aspects. For example, there is one on managing of unexpected in decommissioning. There is very useful tech doc on data analysis and collection for costing of research reactor decommissioning. We even developed software for it. Yes, managing the decommissioning after an accident, decommissioning at multi-facility sites. And one of those latest reports is about global status of nuclear decommissioning. So these are just examples. You can have PDF files for free without any problems. And if you will be here, I can give you even hard copies for your libraries. Next slide, please. Another point that I introduced were also safety standards on decommissioning. So the most important one is on general safety requirements, GSR Part 6, and based on this are built different other safety standard series, so-called specific safety guide. So there you can see one that was published in 2018 on decommissioning of nuclear power plants, research reactors, and other nuclear fuel cycle facilities, so bigger facilities. Another one from 2019, decommissioning of medical, industrial, and research facilities. And there are also other examples of specific safety guides on safety assessment and release of the site from regulatory control. And there is one on application of concept of exclusion and exception and clearance. And from this one will be 2 reports, two safety standards, one on, maybe you can click the next slide. Yeah, I think that it is there. Next slide, please. Okay, jump a little bit. There will be new safety standards report this year on one of exclusion concept and second one on clearance concept. Yeah, those safety standards, decommissioning of nuclear power plants, research reactors, and other nuclear fuel cycle facilities, they provide more point small considerations that are specific to those facilities. So those are built on GSR Part 6, but provides more on planning or conducting or implementation, on completion of decommissioning, and also on termination of authorization for decommissioning of facilities. Next slide, please. And this specific safety guide provide guidance on decommissioning of medical, industrial, and research facilities. So smaller facilities, but they may have also interesting like operational history and may cause challenge for decommissioning. But usually they are smaller, so there is acceptable simplified approaches to the decommissioning, and there are some guidance and some implication of categorization scheme in the regulatory review of decommissioning. Next slide, please. It is what I mentioned already. So this one safety series report on exclusion, exemption, and clearance will have two new ones that are about to be published very soon this year. Next slide, please. Then, in addition to like main safety standards, basic safety standards, there are also reports on safety report series that provides more, like I would say, technicalities, technical information to implementation of safety standards. Here are examples. I will not stop in details of on all of them, but those provide, examples of some specific dismantling strategies, for example, safety enclosure, on specific phases, for example, transition, on publications, I mean, decommissioning plans, safety assessment, you can see there, management of the project risks, and methodologies for assessing the induced activation sources. So there are more such reports available, and they provide more like information in support of technical implementation of technical standards. Next slide, please. Other publications, here is the example of TechDoc on model regulations for decommissioning of facilities. So it is really for member states that are new in this area. They need to establish the regulatory regime for it, and this report can give good insights into it. Next slide, please. Connect platform, I think that I mentioned already, Connect platform. So everybody can be a member and access members areas that are more detailed information about events and activities. Next slide, please. Well, we have developed a suite of supported tools, like e-learning tools. First of all, these ideas about have a network, international decommissioning network and environmental remediation network was later followed by other sections and divisions in the agency. So you can see there a small picture, like overview of different networks. So we have now networks for knowledge management, for disposal facilities, for laboratory facilities, for spent fuel management, etc., etc. So you can see all those blue dots are network for something else, and those scientific secretaries do have their own web space, and they can organize their work to interact with counterparts. In addition to that, we recognize that to publish the report, like hard copy report, takes some time. And we started to develop something what is called a wiki, nuclear wiki or decommissioning wiki, with collection of case studies, description of technologies, and glossaries and definitions, etc. So it has now a little bit different phase because it was meantime upgraded, but the idea is like this, to have something published in the Wikipedia style. Next slide, please. This is the map of e-learning materials, e-learning modules that we have developed for different areas of nuclear backend cycle. So for decommissioning, for example, we have 8 modules in English and in Japanese, but we do have many other e-learning materials for disposal, predisposal, disuse yield radioactive waste management, for environmental remediation, etc. Some of parts are even multilingual, you know, in Spanish and French, maybe something the new is also in Russian. This material needs to be, you know, it existed, everything is accessible to you, but it needs to be upgraded, updated, because there are not only new technical developments in our areas, but there are also new developments in IT areas. So there are like new, more attractive approaches, and I don't know, 3D videos, you know, and various other things that I'm not good in, but IT experts they are. So, for example, we have under the development, under the upgrade and update all the decommissioning modules. So next year, towards the end of next year, we will have new ones that will be more attractive, with more information, with more developments described, etc. Next slide, please. Yes, it is the example of the nuclear wiki. So now it looks like this, but there is still some improvements, and we have the hundreds of case studies and glossaries and technologies, etc. Next slide, please. Here is the overview of those e-tools I already mentioned. So networks, e-learnings, nuclear wiki. In addition to that, we have also databases. I likely mentioned it, but I will repeat again. We have at the agency website, and you have full access. You do not need to be even registered to a database that is called PRIS, Power Reactor Information System. So it will provide really recent information about operational power reactors, but there is also decommissioning module that provides information about the reactors shut down for decommissioning, some technical details, some graphs. It's possible to create forms, so it is quite useful. Then we have research reactor database that also includes information about research reactors shut down for decommissioning, and something similar is also for nuclear fuel cycle facilities, and they are quite updated. There is really fresh information. And other databases that you can see here, like SWIFT, etc. So those are databases that provides information about the amount of radioactive waste accumulated worldwide, amount of spent fuel worldwide accumulated, and any other like useful database information. Next slide, please. I mentioned decommissioning peer reviews. Well, if you will open agency website with the description of peer review services, you will see their long list of different peer review services from different areas, safety, security, operational items, many other things. So this Artemis is specifically for spent fuel and radioactive waste management, for decommissioning, as you can see, and for environmental remediation. It is kind of mandatory peer review for European Union countries under the EC directive, but can be also implemented for non-European countries. For example, we did for JEA in Japan, or something limited for Brazil. And because it is a peer review, so those peers are counterparts from other countries, from other facilities that can provide some useful advice to facility in some specific country. So agency role is to organize it and coordinate it. We have always the role of coordinator and deputy coordinator. But the main experts that are providing advices, recommendations, suggestions, there are really peers, counterparts from the other member states. Next slide, please. Artemis is somehow, safety oriented and well structuralized with guidelines, peer review, but we can offer something what we call tailored services. So really peer review that is organized based on the urgent needs of some country. Here are two examples. First one is decommissioning peer review of Japan's mid and long-term roadmap towards decommissioning of Fukushima Daiichi. So we organized already several such peer reviews, and more is probably will come in the near future. And second example is the peer review of Indonesian BRIN, what is a National Research and Innovation Agency. Review of their program of decommissioning and storage for radioactive waste and spent fuel from their research reactors. I was coordinator of this. It was implemented last year. And in this case, agency always play important role. We coordinate it, we organize it, but there can be experts can be mixture of the IEA staff, like professionals, experts, and international experts. So there is a more flexibility for such peer reviews. Next slide, please. Future outlook. So here are some, brilliant ideas for the future. What is necessary to improve? I think that I mentioned it as one of the outcomes of the decommissioning conference. There is work to be done on legal and regulatory framework to have it somehow more adaptive, more flexible to accept future decommissioning demand. Then integration and optimization with waste management. It is certainly very important because it's a matter of fact that decommissioning produces the waste, and it must be properly minimized and managed. Then I hear mentioned various improvements in project management, in funding, planning, and risk management, with use of advanced IT tools and advanced project management approaches. Innovations that actually supports the previous points, and human resources. I think that it is crucial, it is the most important to prepare proper human resources for the future needs. Of course, that like commercial market can offer some capacity in this regard, but I think that it is a responsibility of every member states to recognize their own national needs and to support human resources development in the country. Next slide, please. Robotics, remote handling technologies, it was widely presented and mentioned during the conference. So here are some examples of recent development: laser cutting on robotic arm, a maestro or remote carrier. There are now variety of other robotics applications, various tools, so autonomous robots. Use of drones is also possible for characterization, or I saw elsewhere like robotic dog that can run around the nuclear facility and provide radiological mapping. So yeah, there is a lot of to be developed in this area. Next slide, please. Actually, in line with this is hardware are robotics, and software is environment of virtual reality and 3D simulations. They can certainly support preparation and optimization of decommissioning facilities, as well as communication with stakeholders, with regulator or with the public, to show them what is going to be done, because you can hardly invite everybody to see primary circuit of a nuclear power plant and to show them, that what will be done. But in the nice 3D picture, you can show it quite well. And there are many institutions, research institutions, quite developed in this area, and they can really demonstrate quite a good approaches. It is later. I cannot show you the video because it's too big and I do not have it easily accessible. But it's impressive to see example of real activities that were done based on simulations, real activities, and compare them with the simulation. So it is very impressive to show that this concept actually very well works. Next slide, please. Okay, it was the last one. Sorry, I quickly ran through it. but you know, I completed the slides that were left from yesterday, and you might have now some questions.
Thank you very much. Thank you very much to join us today also. So some more question, dear colleagues. Yeah.
Hello, thanks for this nice presentation. I will not ask anything about this presentation, but as far as I know, you are a counterpart of the IA project, and here we have many candidates that maybe don't know how to apply these CRPs, events. A little bit, maybe you can give about information how to apply over InTouch Plus and so on. I'm also counterpart for a project in Turkey.
You mean TC project, right?
Yeah, TC project, yeah.
Yes. You were frozen for like 3 seconds, but if my understanding is correct, you would like to have like information how to be engaged with the TC activity.
Yeah.
Yeah, very good, very good. I've got it. Yes, I think that I introduced that we have here a Department of Technical Cooperation. So we have really ongoing several technical cooperation projects that includes decommissioning aspects, might include also radioactive waste management. I can give you some examples. And in addition to that, there are other national, regional, or even interregional technical cooperation projects. Then during implementation, there is a need to somehow deal with decommissioning, and we can like jump in when necessary. I was involved in many technical cooperation projects as a somebody who is called technical officer, so in charge for organization of such events. I can just mention countries. Maybe some countries will be there even like, and it will be not a exclusive list of the countries. I will forget for sure. Armenia, Georgia, I mean Caucasian Georgia, not US Georgia, of course, Bangladesh, Ukraine, Indonesia, Kazakhstan, Israel, even Lithuania, Baltic countries in general. So yes, many like technical cooperation with countries. China, I forgot, for China, it is also a big project. And for the coming years, I think that what is certainly in coming year, because now will be end of biennium cycle, coming year for sure, what is in the list is Kazakhstan, Egypt, Indonesia, China, Ukraine, something else. Yeah. So question, how to be involved? First of all, every country has established position a national liaison officer. So it is the person in the country that is like in charge for communication with the agency. Those are formalities, you know, because we have also our project management officer that is responsible for the country. So they are like communicating each other. However, if you know that such project exists, and you would like to, your institution would like to, for example, have support in organization of scientific visit or expert mission or something like this, I would suggest you, without any big formalities, write directly to me. I am absolutely fine if Andrei will provide you with my email address, and I either will directly able to help, or if it will be somehow activities in area of other section, for example, our sister section here, waste technology section, I can guide you to them. So I'm always supporting of the direct contact. It is the best.
Yeah. Okay. Thank you. Thank you very much. So maybe some questions. Yeah. Oh. Okay. So thank you very much, Vladimir.
You are very welcome. I hope
you.
that I filled the missing time. And yes, once again, sorry for this yesterday interruption. It was really totally out of my control. And I'd like to wish you now you have like, I do not have your watches, 4 p.m., right?
Yeah.
In Moscow, yes.
Yeah.
Well, I'd like to
Wonderful.
wish you to have a nice rest of the afternoon. If you send me a link also for tomorrow, maybe I will be connected as well, just to see, just to have some connectivity. And on Friday, unfortunately, I will be out because of some other private matters. And I wish you to have a good completion of this course.
Okay. Thank you once again. Thank you.
Thank you. Goodbye.
Bye-bye. See you.